Well, here's how we're going to do it tonight. The format we like to use, and we'll be just taking a couple of minutes here. I have some announcements and updates to bring you all up to speed on what's happening in the club, and then I will rapidly turn it over to our program chair, and we'll get going with the main event. And then that can easily go an hour, and we have expectations of an hour, but if it goes over, that's totally fine. And there may be some questions at the end if you're willing, Dr. Spalding. After that, we'll take a quick break and then ask everybody to come back promptly. And then we'll get into what else is going on in the club, astronomy by and for members, including an Unjournal Club presentation by Surabhi. And we'll talk about what else is going on around the different corners of the club. So having said that, we do continue to miss Peyton Hall, our home away from home. We're exploring options right now to get away from this Zoom aspect, although we don't expect to move out of the Zoom world in this spring session. Really only 3 more meetings being lined up, but at least there's some hope for the fall to get back either on campus or at least somewhere else in the Princeton area where we can convene. So we'll keep you posted on that. But as of right now, turns out it's not only the COVID situation, but the parking renovation and construction job going on right across from Peyton Hall has thrown a wrench into the monkey works there. So we'll see as time goes on how that's all going to shake out. A couple announcements are just to remind you all that the AAAP merchandise shop is now online and it's working quite well. And a few of us have already received our first orders. Probably takes a few weeks for an order to come in, but they're fairly accurate, it seems, in telling you when your shipment will arrive. So check it out. You can hit the link on the right-hand side of our home page on our website. There's a little hat logo that Surabhi cleverly stuck in there. That's the link to the merch shop, and the password is Sidereal Times with the capitals on the 2 words there. 1 word, Sidereal Times with the capitals. I was just mentioning a couple other things I thought was pretty cool this month. Sky and Telescope magazine in the February issue has an article, I think it's on page 26, on Derek Pitts and the Franklin Institute and all the really good outreach that they're doing there in the middle of Philadelphia. And it's an interesting read, and it reminds me, it's been quite some time now, decades, but we actually once had a star party up at Grover's Mills, north of West Windsor there, and Derek Pitts came to our star party, and we had our club telescopes out in the field, and it was heading towards Halloween, and I'm forgetting the year, 19, maybe Bill will remember this, I'm going to say like 98 or something like that. So one other thing to mention on that same issue of Sky and Tel, I'm very proud to say my colleague in the imaging world has gotten an image published, the NGC 247 Galaxy. Mark Hansen is one of the leads from our Chilean remote imaging group that I've told you guys about. He's really a whiz at imaging, so take a look on page 76. He's using the exact equipment and some of the exact same data that we have, that I have access to. And in fact, here's my attempt to process and develop the image that he has published on page 76 of the February issue. I think mine came out not bad, but take a look at that issue and you'll see a real master at image processing. So kudos to Mark. I wanted to mention again that we've been having a pretty interesting time with our Astro Video live sessions, the winter sessions now. We've successfully convened on 2 of the months, and we're going to do 1 more before we open up the spring session. So March 4, mark your calendars. We hold these sessions whether it's clear sky or not. Of course, we can't do observing if it's not a clear sky, but we will discuss astrophotography and related issues if it's cloudy. So the Zoom link goes out in advance. Last Saturday night, February 4th, we had about 21 of us on the session, and we have been successful in getting more and more of our members to get involved in this. So the concept is, if you can do observing and you can get your rig set up with one of these newer, especially the newer CMOS cameras that are so great for rapid imaging, what we call EAA, for downloading your images and in real time displaying on your laptop. And if you can figure out how to get an internet link from your site out in your backyard, we can run this right into the Zoom live feed. And last Saturday, we had all these scopes online. Actually, Rich from Florida was not online with the Skywatcher because he was clouded out. We had better weather than Florida, but the rest of them were. And I'm not going to mention who owns all these scopes, but except for the one on the upper right is the Club telescope out at the observatory in Washington Crossing Park. Your scope in the bottom left, we've got room for more. Let's keep this trend going. And if you're interested and want to learn more, then the folks in this club are ready and able to give you cheap advice. Flip me an email or Dave Skitt or any of the others who are involved in astroimaging, and we can help you get further down that path. We can talk about that more after the break. You might remember last month, I tossed out a pretty stiff challenge for the observers in the club, and that was to attempt an observation of the near-Earth asteroid 7482 with the acronym 1994 PC1, which was interesting because it was coming within about 1.2 million miles, a very close, almost a grazing of the planet Earth. And this was going to happen on January 18th. There was a very narrow window to observe it because it was coming in very faint until right about January 18th. And then there was a window of observing it about 2 or 3 hours that night. And then it was going to be really lost in the haze of the southern sky. So I had heard from several of you did succeed, or at least a few of you did succeed. As far as I'm aware, the following individuals get blue stars for the observing challenge, and that would be Dave and Jen Skitt, Tom Swords, Bob Vanderby. Is there anybody else amongst the group here that successfully hit the challenge here and made it? Speak up now. Get your glory. Maybe not. Well, that's something now. I was able to photograph it with my rig, and it was interesting because it rained really hard the 3 days prior, and going into that January 18th, which was a Tuesday, it looked like there was going to be no chance. And then the day of January 18th, the clouds parted, and right about literally about 5 p.m. as the sun was setting, it became totally clear. And I was able to find it on my my home observatory here, and I got this image, a 10-minute image in which the asteroid appears as a streak. Look how fast this thing is moving in 10 minutes across the star field. And you can see it was about a magnitude 10 event. You can see the magnitudes of some of the background stars. I thought it was kind of cute that it picked up, the image picked up a galaxy about a magnitude 15, according to the star chart there, that little fuzzy blob there. Moreover, though, to make the challenge even more, to meet that challenge in a more thorough way, I was able to take, let's say, turn my subframes into a movie. And we can talk later about how this is done, but let me just play a little session here. Now, here's the asteroid here moving from the upper lower left. This is 10-second subframes stitched together into a movie, an MP4 now, a total elapsed time 11 minutes. You can see how fast this booger was moving. Every 10 seconds is one of these jumps, every 10 seconds. Well, that got me to thinking, exactly how fast was it moving? I hope I'm still sharing, am I?
Yes.
Yeah, it got me to thinking, just how fast is this moving? And can we use the data that can be collected so elegantly with these modern astrophotography tools that we have available to us? And here, a color CMOS camera connected to a pretty nice telescope. With the image that I just showed you, why not try to calculate the speed? And it occurred to me, staring at this, that the streak across the sky in this 10-minute image really represents, if you think about it, could be considered the third leg of a triangle. And we could consider it a right triangle and use the Pythagoras theorem to calculate how long this streak is that took place in 10 minutes, and that would be c² in the calculation here. This is actually the angular distance that moved, and that gives us an angular velocity. We could calculate, because we know from the camera specifics and the position on the XY frame of the image axis of the image field here, we could calculate that the asteroid moved 2,646 pixels in 600 seconds. And we know the image scale of the sensor and the optics is 0.46 arc seconds per pixel. Therefore, the asteroid moved 1,218 arc seconds in 10 minutes, or 2.03 arc minutes per minute. Now, that's an angular velocity, and we can convert angular speed to linear speed through this equation. It's simple algebraic expression. The angular speed is equal to the angle of rotation in radians, and t is the time. So we've got all the data we need. So the angular speed, 2.03 arc minutes per minute, works out to be 0.035 radians per hour. And then thinking about our long forgotten algebra and geometry, we could actually convert angular velocity to linear speed through the simple equation of velocity equals omega times r, where omega is the angular speed and r is the radius. And again, if we think about this model, the distance of the asteroid from us was reported by the professionals to be about 1.2 million miles. So with that as a given, and the radians per hour calculation up here, I ended up with a value of the speed of the asteroid of 42,500 miles per hour, which to me came surprisingly close to the reference value that I got off one of the websites, and checks out by the professional astronomers came in around 43.7, less than a 3% error from using home amateur astronomy equipment to calculate the speed of an asteroid. And to put this in a perspective, the moon's orbital speed given here is 2,288 miles per hour. So this asteroid came in within 1 million miles of the Earth, moving at almost 20 times the speed of the moon. To me, that's just a mind-blowing finding from this little challenge. Anyway, that's the kind of fun you can have doing amateur astronomy. If that's not enough for you, you're going to get more as we go on. And I'm going to stop here and stop my sharing and turn it over to Victor, who's going to bring up the main event of the night.
All right. Well, our guest speaker for tonight is Dr. Christopher Spalding, who is the 51 Pegasi B postdoctoral fellow at Princeton. And tonight's presentation is our upside down, or the upside down, inside out solar systems. During the past decade, of course, we've explored many exoplanets, and it's revealed a puzzle. Many of them seem to orbit backwards, opposite to the spin direction of their host stars. It seems counterintuitive. How can this be? Moreover, these worlds usually exist 10 times closer to their stars than Mercury does to the sun. Clearly, something very different led to the creation of these upside down, inside out systems as compared to our solar system. In this talk, Dr. Spalding describes the weird and wonderful properties of these alien worlds and discusses what they may be teaching us about the origin of our own planet Earth. A few words about Dr. Spalding. He earned his BA and Masters of Science degrees from Cambridge University with first class honors, and his PhD in planetary science from Caltech. He's won numerous honors and awards, including the Ray Duncombe Prize for Dynamical Astronomy, a NASA Earth and Space Science Fellowship, Graduate Fellowship in Earth and Planetary Science, and of course the 51 Pegasi B postdoctoral fellowship, and most recently and closer to home, a Lyman Spitzer Jr. postdoctoral fellowship. Dr. Spalding's primary research seeks to understand planet formation by way of simple theoretical descriptions of planetary dynamics. He enjoys applying simplified mathematical models to extract important lessons from problems spanning planetary system formation and architectures, Earth's long-term habitability, extinction dynamics, and more. He's active in science education and outreach as a teacher, guest lecturer, and colloquium organizer.
Well, thanks for that wonderful introduction. And Rex, thanks for that lovely application of mathematics in an everyday setting. That's very impressive. So can you all see my screen?
Yes.
Okay. So hello, everyone. It's great to be here with you virtually. As Victor said, I am a postdoc in the astronomy department at Princeton. And even though my official title is 51 Pegasi B postdoctoral fellow, that is just a title. That doesn't mean I only work on that one planet. I work on other planets. So mainly what I do is I'm a theorist, and that means I don't actually look through telescopes. All of you probably know a million times more about telescopes than I do. I mostly talk to my friends who actually use telescopes, and they tell me about funny things they've seen in the sky. And then I use math and computers to try to understand what's going on. That's essentially what a theorist is. So my talk today will be mostly about what those mysteries are, rather than necessarily, I'm not going to throw a bunch of math at you, but hopefully you'll get a picture for what my title means, upside down, inside out solar systems. It essentially alludes to the fact that planetary systems we find around other stars are often very different from what we know around our own stars. So I wasn't entirely sure what level to pitch it at. So if I go too fast or too slow, just let me know. And feel free to interrupt with questions or whatever your regular protocol is. So to get going, you're all very familiar with this kind of a view, looking up at the sky and seeing all the stars move across from east to west and east to west and east to west. And I wanted to start from here because I like to think about astronomy as essentially humans looking at the sky, looking at the stars, and seeing what happens and then trying to understand what they see. And one of the most remarkable things I like to think about is that humans have looked up at the same sky essentially unchanged for millennia. This picture could have been taken, 2,000 years ago, and it would be the same person looking up and wondering. And in some sense, the earliest mystery is why all the stars go from east to west. Like, of course, we know today that the Earth rotates. Any great scholar will tell you that the Earth rotates. But it's interesting to think that for a while, just the simple fact that the Earth rotated, and that's why the stars move across the sky, was debated by the biggest scholars of the day. So I am not a historian, but I did go into the history of this a little bit. And it goes back to ancient Greece. And I did not tell Rex about this, but he independently mentioned Pythagoras. I was going to mention Pythagoras because back in ancient Greece, about 400 BC, there were kind of two schools of thought. There were the Pythagoreans, who included Pythagoras and a whole bunch of his followers. They seemed a little cultish, but they were a band of scientists. And they thought that the Earth rotated. They thought that the Earth spun around on its axis once per day, and that's why the stars move across the sky, which to us is like obvious. I mean, why would it be any other way? But Aristotle, a little bit later, another name you may have heard of, he was big and shouted louder, and he said, no, like the Earth doesn't rotate, that's silly. Like, why would you think that? And he proposed this idea that the Earth is stationary, and there's this giant celestial sphere with all the stars studding it that rotates. And this seems silly to us now, but from the observations that they had in that day, no telescopes, no nothing, it seems a pretty reasonable assumption because that's what it looks like. It looks like the stars are going across the sky. So even though Aristotle was wrong, no one could really fault him because he was working under the observations of the day. And that's essentially how science progresses. You have an observation and you try to explain it, you get it wrong, and then new data comes in to show you why you're wrong. So over time, this notion that the Earth rotated, gradually the light bulbs started going on in different cultures across the globe. Astronomers in India apparently cottoned onto this in 500 AD, and then it spread to Islamic astronomy in 1000 AD, and it actually took a little while. It took 500 years later for this idea to spread to Europe. We often hear that Copernicus was the one that sort of said that the Earth rotates and everything goes around the sun, but it was more of a slow burn across the globe, this realization that the Earth rotates. And again, of course, it's a trivial fact today. But Copernicus was essentially saying that in order to explain the stars and the planetary motions that do these weird loopy things across the sky, we need a simpler model. And that simpler model was the Earth's rotation, much simpler than this big sphere and everything. And that's essentially how all science progresses. You start with a complicated idea that seems to fit everything, but then it's someone who comes in with a simpler idea that makes sense of everything. And it's like, why didn't I think of that before? So, of course, you all know that the Earth rotates. But this very simple realization made sense of so much on the world. So I'm showing here the Earth, and I'm showing currents on the Earth, so ocean currents. And atmospheric currents are pretty much the same. And I personally am very thankful that the Earth rotates. The reason is, and I'm thankful that it rotates counterclockwise, because if you look at all these currents, the red ones are warm and the blue ones are cold. If you look at the North Atlantic, some of you may know that there's a warm western current that brings hot water up from Florida and then across the Atlantic, and it keeps Europe much warmer than Canada. And if you can't tell from the accent, I am from Northern Ireland. And I grew up in an environment where I could go out in the winter with a thin sweater on and not be freezing. But if you go across the same latitude to Canada, you end up in Newfoundland, and their winters you couldn't go out without, a tank protecting you because you'll freeze. And this stark difference between climates at exactly the same latitude on the Earth is all because of the Earth's rotation. And scientists have actually done the experiment where they set up a model of the Earth and spin it backwards. And this picture reverses. Europe freezes and Canada becomes warmer. So I'm very thankful of the Earth's rotation. So there's one more aspect of the Earth's rotation I would like to say. And the reason I'm focusing on Earth's rotation is because we're eventually going to look at the sun's rotation. But one more aspect of the Earth's rotation is that which gives us the seasons. And this is a property known as obliquity. So the Earth isn't just spinning. It has its orbit, which is the yellow line here. And this plane is called the ecliptic plane. And if you imagine the Earth is spinning and there's an axle through the middle of the Earth, that axle is tilted with respect to this ecliptic plane. And this causes the Earth to tilt its north and then its south and north and then its south closer to the sun, getting more direct sunlight and less direct sunlight, more direct sunlight, as causing the seasons to come and go. If we didn't have any obliquity, didn't have any tilt, then we wouldn't have any seasons. We would just have a constant climate throughout the year. And counter to that, if we had a 90-degree obliquity, we would have super intense seasons. Everywhere on the globe would be 6 months of dark and 6 months of light. So this properties of spin and obliquity are critical for the Earth and its environment and everything. So the obliquity of the Earth is about 23 degrees. And you may or may not be surprised to hear that scientists don't really have an explanation for why this is 23 degrees. It's there's no reason why it should be 23 degrees instead of 0 or instead of 90, but there's no sort of self-consistent idea that explains why the Earth's obliquity is 23 degrees. It could have been anything. But if we could understand where this obliquity came from, that would tell us a lot about where the Earth came from, because obliquities don't change a whole lot over time. So whatever the obliquity the Earth has now, it probably had 4 billion years ago when it was being formed. And so something about that formation process locked in this obliquity. So it exists as a kind of fossil remnant of the Earth's formation, telling us something about the baby early Earth. So we can zoom out and do this exercise with all the planets. So not only Earth, but all the planets in the solar system, with honorable mentions here, Pluto and Ceres, in the top right and top bottom right, or top and bottom right. They all have their own obliquities. They all have their own tilts with respect to their orbits. And some of them are kind of like the Earth. So Saturn is about 25 degrees. Neptune is about 28 degrees. So some of them are very similar to Earth, implying there may be something similar going on there. But I'm going to direct your attention to two oddballs that you may be aware of. This is Venus and Uranus. So Venus is peculiar for spinning backwards. So if we go back to that picture of a spin axis, where on Earth it's pointing up, Venus is pointing upside down. So its spin axis is pointing upside down, which is another way of saying it rotates backwards. And again, we kind of have a handle on why this might be, and it tells us something about the history of Venus. Essentially, its atmosphere is really big, and it's being tidally spun up by the sun. That's a whole other story. Uranus on the right here is tilted not upside down, but over on its side at about 90 degrees. And again, this sticks out. And if we can understand where this 90-degree tilt comes from, then we can understand something about Uranus. And it just so happens that for Uranus, there is a favorite explanation as to why it's tilted over on its side. And the picture is that whenever Uranus was first born, it probably had a spin axis that was pointed up, sort of perpendicular at right angles to its orbit. But whenever astronomers see something funny, quite often they just propose that a big rock slammed into it. And that's the idea for Uranus. The idea is that Uranus got hammered by something bigger than the Earth early in the solar system, and that knocked it over, like 10-pin bowling. And this is important because we don't have a lot of bigger than the Earth rocks flying around the solar system today. So if Uranus got struck by one of these things, it means our solar system used to have these big planet-sized chunks that are no longer here today. And that tells us something very, very critical about the solar system's evolution. So there is a lot that is locked up in the spin axes of the planets in the solar system. So I could give you an entire talk about spin axes of planets, and I think it would be an interesting talk, at least to me. But I'm going to talk to you now about the solar system at large and how this idea of spin axes and tilts can apply to entire solar systems. So if we look at our solar system, this is just an image of our solar system. Nothing is to scale here, but I'm showing you this picture of our solar system where the white lines are the orbits, to show that the solar system is very well ordered. So all of the orbits are in the same plane. It looks like a giant record with the planets kind of scoring out a track in the record. I'm too young to ever have used records, but they're coming back into fashion. So I actually just got my mom one for Christmas. So some people are still listening to them. But anyway, the planets are scoring out disks in a record. And this is unusual. There's no sort of reason to suspect that planetary orbits need to all orbit in the same plane. The laws of physics allow them to orbit in any plane. So something arranged these orbits in a flat plane. And this flat plane, incidentally, is why you can sort of see that the planets in the night sky often follow on the same line, on the ecliptic line. This is essentially down to the nature of the solar system being coplanar and the circles being essentially concentric in the same plane. So one more aspect of the solar system is that the orbits are well aligned. But let's go back to that thing I mentioned earlier, obliquity. But let's think of it in terms of the sun. So the sun is also rotating. This has been known for hundreds of years that the sun is rotating. It's seen through sunspots going around. But the sun itself, you can define an obliquity. So there's a plane that the planets are in, and then you draw right angles to that. And the sun is tilted with respect to that by 7 degrees, 6 or 7 degrees. Now, this is kind of small. and you'll see it's small compared to exoplanetary systems. But it's just like the Earth, the 7 degrees needs some kind of an explanation. Why is it 7 and not, 70? That's actually unsolved and something that I have worked on. But again, if we, knowing where that came from tells us a lot about the solar system. So the idea is to try to solve this kind of well-aligned nature of the solar system, the planets all being in the same plane and the sun spinning in the same direction as them. So everything is counterclockwise, the orbits and the sun. These ideas go back to the 1700s. So the earliest reports of someone sort of trying to solve this mystery of why all the planets are in the same plane is this dude Swedenborg, who was indeed Swedish. If he wasn't, that would be confusing. And he has these drawings here that are, hundreds of years old. On the top left of like the sun-like thing in the center and this like crust. And then if you look down on the bottom left, the crust is kind of budding off into all these little spheres. And on the bottom right, that crust has broken apart into planets. And these were the earliest ideas that the planets are in a flat plane because they formed out of some kind of a disk, some kind of thing that looked like a record. But this idea, well, first of all, I'll say Swedenborg, partly for his scientific ideas, but also partly for his spiritual ideas, has earned quite a cult following. And I find there's actually a Swedenborg Foundation that has a website, including this little donate tab. I would not advise you to necessarily donate to them, but for some reason, people are really into this Swedenborg guy. But he had a good idea about planet formation. But this idea of why the planets formed in a disk, of that the planets formed in a disk, was really solidified by this guy, Immanuel Kant. And Immanuel Kant first put together the idea that the planets are in a plane because they formed out of a giant disk that had rocks and dust and gas swirling around the early sun. That was Kant's sort of claim. And that, in some sense, is the longest standing correct idea of planet formation, because this is correct. This is what we know how planets formed. They formed in these big disks of gas and dust. There's the modern version of this idea is known as the Nebular Hypothesis. And the story goes as follows, that somewhere out in space in the top left, there's this giant nebulous cloud. So a nebula just means cloud. This giant cloud of material, and something, maybe an exploding star or something, perturbs it and causes it to start to slowly collapse under its own gravity. That's from the top left to the top right. And I don't know how many of you are watching the Olympics, but the figure skaters there, whenever they want to spin faster, what do? They pull their arms in. And the exact same thing is happening in this cloud. As it's rotating, as it's collapsing, it's got a little bit of a rotation, but as it's pulling itself in through gravity, it starts to spin faster and faster and faster and faster and faster until its material is spread out into a disk in the bottom left. The center still ignites into a star, but the stuff that was spun off is forming this disk that Kant predicted hundreds of years ago. And then out of this disk, the planets coalesce through processes that hundreds of PhDs are being given to understand, that we still don't fully understand. And this is why they're in a flat plane, because they formed from this collapsing cloud that went into a disk. So these disks, they've been known to exist for a long time, but not until recently have we achieved spectacular images of them. So often what you see in press releases, I've noticed, of scientific findings are like artistic impressions or digitally enhanced things. These images here are direct images of protoplanetary disks from a telescope called ALMA, at a kind of a large millimeter array, if you're interested. And each one of these disks is its own separate planetary nursery forming its own planetary system. If you notice this one on the top right here, the most famous, It's a disk with all of these grooves cut out of it, just like the solar system. And although there is debate, the leading hypothesis, the leading idea for what's causing these grooves is little baby planets forming and sort of eating up all the material in that ring. They almost look like Saturn's rings. If you've ever seen a close-up of Saturn's rings, it has a lot of gaps in it from little moons eating up all the material. So this idea, hundreds of years old, is spectacularly shown to be correct. But one more aspect is, now that we can see these disks, we can learn things. And one in particular thing that you can learn from these is that if you look at the center of the disks, it's brighter than at the edge of the disks. And this makes sense because these images are in infrared. And so for anyone who's ever put on infrared goggles, things that are hotter are brighter. So the fact that these disks are hotter in the center than at the edges means that they're hotter at the center. This makes sense because there's a giant star in the center that's heating everything. So looking at the sort of structures of these disks, we can start to look back at our own solar system and say, okay, what can we explain about our solar system, given that we know it formed in one of these disks? And so returning to our solar system, there is an interesting, so they're all in the same plane, as I mentioned earlier, but there's also this kind of interesting divide that you may or may not have noticed before, in that the close-in planets are smaller. So Mercury, Venus, Earth, and Mars are small and puny. Even though we live on Earth, it's tiny. And there are these giant planets on your right-hand side. So Jupiter, Saturn, Uranus, and Neptune. Pluto is minuscule. These are actually these planets are to scale in this drawing. So it really gives a sense for how much bigger Jupiter is. And if you look at the disks, astronomers have come up with an explanation for why there are big planets on the outside and little planets on the inside. And it's back to the fact that the disk is colder on the outside. So I've drawn this white line here. The white dashed line is called the snow line, and exterior to this line, so if the sun is on the left here, exterior to this line, things are cold enough that literal snow can form in the disk. So it's back to that Canada picture I showed earlier. There's a bunch of snow on the right-hand side. Whereas on the left of that line, the disk is so hot that all water is just in the steam phase. There's just too much heat to cause any snow. And this is important because giant planets are thought to form by literally a whole bunch of snow packing together under its own gravity and stickiness. You know, if you roll a snowball, it gets bigger and bigger because it's sticky. And eventually, once that snowball, the iceberg here, gets to something like 10 times the Earth's size, so it needs to get really big. If it can get to the 10 times the Earth's size, there's a very interesting physical process that kicks in, and the iceberg starts sucking in all the gas in its vicinity. It's a complicated physical process, but it's well understood. And once it starts sucking in all its gas, it balloons up to something the size of Jupiter or Saturn. Neptune and Uranus are more sketchy to explain, but Jupiter and Saturn undergo this process. The thing is, about the interior of the disk, because all the water is evaporated, there isn't enough snow to pack things together. So things stayed as small as the Earth, which isn't big enough to suck in all the gas. So we have this sort of good explanation. We have this good explanation for the solar system. It's coplanar because it formed in a disk from these collapsing clouds. It has big planets on the outside because it's colder and small planets on the inside. And the star is spinning in the same direction from the planets because it was born out of the same material as this disk. So everything was spinning in the right direction. So now we return to this picture. Whenever I showed you this picture before, we were mere nomads 2,000 years ago that didn't even know the Earth rotated. But now we know exactly how the solar system formed. So now what we can do is we can look at these other stars and ask whether they have planetary systems that are the same as ours. And as I've alluded to with the title of my talk, the answer is that a lot of systems don't look like ours. And now we're going to sort of look at what that means about our own solar system. Because what I've painted before is a pretty believable picture. So the fact that some exoplanets are going to deviate from that is teaching us something. But first of all, many of you have probably heard how we detect exoplanets, but I think it's important just to revisit briefly how planets around other stars are detected. And the first thing to notice is that it's really hard. So stars are bright. The difference between the Earth's brightness and the sun's brightness is a factor of 1 billion. And I actually looked up the brightness difference between the headlights of a car and a firefly. And that's actually 1 million. So the contrast in brightness between a firefly and a car is actually still 1,000th as much as the contrast between the sun and the Earth. So that's how difficult it is to see the Earth. It's as if there was a teeny tiny firefly right, driving this car towards you for some reason. So planets are almost never, except in very specific circumstances, are planets sort of photographed like those big disks that I showed you before. We need to be cleverer in order to know that there are planets around stars. And the sort of arguably the most successful has been the so-called transit method. So many of you have probably seen the transits of Mercury and the transits of Venus across the sun. And the exact same idea is applied to study exoplanets. So if you stare at a star long enough, if it has a planet and that planet's orbit is along the line of sight, then that planet will slightly dim the star once per orbit. And it'll be like clockwork, there'll be a dim, 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 dim. And no matter how long you stare at it with your telescope, you'll see that sort of metronome of the planet getting dimmer and then brightening again. And this is the signature of a planet orbiting around a star. And this transit technique has actually discovered more planets than any other technique by quite a long way. And it's discovering more all the time. So this is the most successful method, but it's actually not the first one that was successfully used. The first one that was successfully used is the so-called radial velocity. And this is going to be a video, it might be a little choppy, but essentially the premise is that going back to the Olympics, but the Summer Olympics, if you imagine a hammer thrower grabbing a hammer and throwing it around and around and around, and imagine the hammer is the planet and the thrower is the star, then the hammer doesn't just move. The hammer thrower moves as well as the planet or the hammer is moving around. And the exact same principle applies for stars and planets. The planet doesn't just orbit the star, it causes the star to wobble backwards and forwards. And we can pick this up by using the principle, the Doppler effect, which you've all heard anytime an ambulance rolls by, gets higher and higher and then lower and lower as the ambulance goes by. Light behaves in exactly the same way, in that as the star is wobbling toward you and away from you and toward you and away from you, it gets blue and then red and blue and then red, blue and then red. And again, just like with the transit, that's going to be a metronomic blue and red, blue and red, blue and red. So if you see a star doing that, you know that there's a planet orbiting it, or there's something orbiting it, but you can tell it's a planet you can often tell it's a planet. And so it's called the radial velocity because you can only see the component of the velocity that's going away from you and toward you. You can't see the side-to-side motion. You can only see it going toward you and away from you. So you need to use this like ambulance approach. So that technique, the radial velocity, was the first one used successfully to find an exoplanet. And it was my postdoc's namesake, 51 Pegasi b, that was the one that was discovered. In 1995, I was 4 years old, maybe 3. I don't remember it. I didn't have my PhD yet, so I didn't have to I didn't study it. But this planet, it was remarkable for a number of reasons, but perhaps the most astounding at the time, and even today, is that I have Mercury here for scale. So the distance from Mercury to the sun is scaled relative to the distance of 51 Pegasi b to its star. In other words, 51 Pegasi b is about 10 times closer to its star than Mercury is. Our solar system is kind of notable because there's nothing between Mercury and the sun. People have looked for centuries. They can't find anything between Mercury and the sun. It's just this empty, barren wasteland with not a rock. And yet we look at this other planetary system and it's got something that's the size of Jupiter. So 51 Pegasi b is the size of Jupiter. And it's piled in this part of our solar system that has absolutely nothing. So something is already different. Here we have the inside out part of my talk. These planetary systems are inside out, meaning there are planets where there shouldn't be planets based on our solar system. This discovery actually recently got the Nobel Prize just a couple of years ago. I mean, this discovery, in addition to a bunch of other things, got Mayor and Queloz a Nobel Prize, which was joint shared with someone else who I've cropped in this photograph because it wasn't an exoplanet person. But, well, it's not a photograph, it's a drawing. So these two got the Nobel Prize, and I believe it is the only Nobel Prize awarded for exoplanetary discoveries. Maybe there'll be more. But so this planet was, it was hot. It was really close to its stars, I showed. So it was super hot. And it was about the size of a Jupiter. And astronomers are in general very creative people. But in terms of coming up with names for planets, they are not the most intelligent. So these were called hot Jupiters. They weren't called hot Jupiter-like things. They weren't called, you know, I don't know, toasty roasties. They were called hot Jupiters. And this naming convention is actually stuck. We've since discovered things called warm Jupiters, which are a little bit less hot. And I even read an article the other day talking about tropical Jupiters. And not a lot of people talk about tropical Jupiters, so I'm glad they don't. They're also cold Jupiters. Our Jupiter is thought of as a cold Jupiter. But these were hot, and this was a mystery. Like, why are they so close to their star? To really put into perspective just how close these planets are to their stars, some of you may recognize this mission. It was launched recently. It's called the Parker Solar Probe. And the goal of this mission was to fly in and touch the sun. So there were lots of headlines saying that this probe was going to touch the sun, touch the solar atmosphere. It doesn't actually touch the sun, but what it does do is it gets so close to the sun that it's bathed in the sun's magnetic field and atmosphere and could be struck directly by a coronal mass ejection or something. It gets remarkably close to the sun. But even this object that humans needed to endeavor to, you know, protect from the heat and the magnetic fields and everything, even this is not as close as many exoplanets are to their stars. So exoplanets are living in this environment that is so extreme that humans are only beginning to be able to get instruments that can even measure it, let alone sort of exist there for a long period of time. So that really puts the hot in hot Jupiters. They're totally unlike anything that we have in our solar system. And there's a mystery with hot Jupiters. So if you remember back earlier in the talk, I mentioned that we know why Jupiter and Saturn are far out, because it was cold there. It was cold there, and there are lots of snow around in the protoplanetary disk. It formed these big balls of snow that sucked up all the gas. Problem solved. But now we go find these Jupiter-sized things that are inside the snow line, and things all of a sudden look a lot more complicated. Our theories for planet formation are thrown on their head by the discovery of these hot Jupiters, because they don't fit with the story that we've built based on our solar system. And to really put this in perspective, this is kind of like going into the Sahara Desert and finding a snowman. It wouldn't be a very happy snowman, but you would be pretty suspicious. You would want to know why that snowman's there and where it came from, because it sure as heck was not built in the Sahara Desert. And this is exactly the idea that that scientists such as myself, and this is one of my main fields of research, is the idea that hot Jupiters weren't always hot. They started cold. So whenever we find a planet, they're usually like 4 billion years old, give or take 5 billion. And so this means they have had a lot of history that we haven't seen. And so the general idea is that these hot Jupiters might have been born 4 billion years ago in the cold outer reaches of their planetary systems. But just like an iceberg that can calve off Greenland and move closer to the equator, these cold Jupiters can migrate inwards and become hot Jupiters. And then we see them in this hot state. So they've built themselves up big enough, just like the iceberg, that they don't melt very quickly when they go into warm waters. So they live there long enough for us to see them. So the question is, what causes what causes a thing the size of Jupiter to suddenly move inwards in the solar system? Is our Jupiter in danger of doing this? We want to know. So an idea to explain how these giant planets can get really close to their stars comes from comets. And so I'm sure some of you might have even seen comets. I tried to see the comet that came by like a year ago, but we have trees that block the horizon. But comets have these very peculiar orbits. They don't look like concentric circles. They swing out from really far in the solar system, come really close to the sun, and then swing out again. And this is why they have these large periodicities. And the idea that to form hot Jupiters is that they formed kind of like Jupiter, so one of these concentric circles, but then some passing star or something came too close to the planetary system and kicked that giant planet onto a comet-like orbit, some really long, elongated orbit that caused it to go close to its star. And then over time, this super elongated orbit would shrink to a small circle around the star, which is how we see hot Jupiters. So this was an idea that was put forward for hot Jupiter formation about 20 years ago, about the same time 51 Pegasi b was discovered. But it's sort of a wild notion. And the way to test it goes back again to obliquity, something I mentioned right at the start of the talk. And so if you recall, the sun's spin axis is tilted from the solar system by about 7 degrees, which is a small number. But if a hot Jupiter formed through this comet-like orbit, then we would expect it to not be aligned with its star's spin axis. Its star would be spinning at some angle to the orbit. There would be some tilt. And so a way to test this idea that hot Jupiters once lived far away and then were sucked in by something is to somehow measure the misalignment between the hot Jupiter's orbit and the spin of its star. Now, this is not an easy measurement to make. It wasn't made until the 2000s, but really not until 2010 was it successfully implemented. And I can briefly, well, in the interest of time, I will skip over exactly how we do that, but I can tell you at the end if you are interested. But the measurement was finally successfully made in 2010. So the measurement, remember, is the misalignment between the spin axis of the star, this white arrow, which here is anti-clockwise. So the star is spinning anti-clockwise. And in 2010, Josh Wynn, who is actually my postdoc advisor, discovered an upside down star. So hot Jupiter, so it's the hot Jupiter here is spinning anti-clockwise, counterclockwise, but the star is spinning clockwise. It's spinning the opposite direction, more or less. This is just like Venus in our solar system. Venus is spinning upside down. So here we have an example of a whole upside down planetary system for the first time. And this, at the beginning, kind of looks like what we expected from the cometary picture that I mentioned. The cometary picture predicts that that hot Jupiters should be misaligned with their stellar spin axis, which is what we see. However, they also have these really elongated orbits, which we don't see. Hot Jupiters typically have circular orbits. They're small, they're hugging their star. They're not super elongated like comets. And over time, it's become apparent that there aren't really any, or there's a few, but not enough examples of hot Jupiters with these really elongated orbits to entirely come about through this cometary pathway. So that's a mystery. So if we go back to Immanuel Kant and his protoplanetary disk, we need to somehow, if we can't just chuck a hot Jupiter in, we need to somehow find a way to make a star misalign with its planetary system without this like violent flinging of giant planets. And so if you imagine a protoplanetary disk, like what Immanuel Kant proposed here, you can think of it almost like a whirlpool. And anything that gets sucked into the middle will be rotating in the same direction as the whirlpool. So if you put like a rubber duck or something in here, it would be spinning the same direction in the center as all the water on the outside. And this is where the star forms. So the star in this picture should always be spinning in the same direction as the planets. It shouldn't be upside down. So if Immanuel Kant was still here, I know what he would say. He would say, this can't be. We can't have planetary systems that are upside down that form from this disk pathway. So my research has essentially been trying to explain how you tilt planetary systems without flinging hot Jupiters at the star from a far distance away. And in order to understand what we might be missing from the picture, so this is science progresses by sort of making an idea, seeing it kind of makes sense, then getting more data, and then seeing it doesn't really make sense, and then trying to come up with a new idea to see what you missed. And by seeing what you missed, you learn something. And so to go back to this nebular hypothesis that came out of Immanuel Kant's work, remember I said that there was this cloud that started to collapse. It started to spin out into a disk. All the planets formed in the disk, and there was a star at the center. So the thing that we missed here is that most clouds don't just make one star. They often make two stars, maybe even three. And it's amazing that we missed this because it's in a lot of sci-fi. Sci-fi loves to put multiple stars around single planets. And we now know that there are plenty of planetary systems that have multiple stars. And we know that actually most stars begin their lives kind of gravitationally attached to another star. The sun is actually unusual in that it doesn't have another star sort of close by. So what if we imagine Immanuel Kant's protoplanetary disk that is just sitting on its own, but now we just sort of imagine there is another star attached to it. So the picture you should have here is that there is a star with a disk around it, and then far away from it, there is a second star that is orbiting that entire thing. So it's like we've got a little fried egg and then a distant ball that's orbiting it. And this is what I worked on a lot in my PhD, the consequences of a picture such as this. And it turns out that this star, this secondary star, causes a gravitational pull on the disk, all that gas and dust that's forming planets. And it's actually able to tilt the entire thing over. You can show this with computer simulations. And if you tilt the entire disk over, the central star actually stays where it is. It still points in the same direction, but the disk tilts around it. And this means that any planets that form out of this disk are, so these disks are kind of like big pizzas being spun out, and the planets form like pepperoni in them. So whatever plane the disk takes, the planets take that same plane, but the star is unaffected. It stays pointing in one direction in the middle. So simply by taking account of the fact that stars are often born with company, they're not often lonely, their disks are often kind of pulled to and fro like a ship on the waves. and their planets end up misaligned with their star's spin axes in the process. So this key element is able to explain these misaligned hot Jupiters without the need for them to be kind of thrown in from far away. So this was an idea that we worked on a little while ago in 2012 or 2013. But in order to, again, to test it, we need more examples of planetary systems. There weren't a lot of examples of these misaligned hot Jupiters, so maybe we got the measurements wrong, maybe there's some nuances that we're missing. So if we fast forward a little bit to 2009 to 2013, this was when the most successful exoplanet hunting mission was launched, Kepler Space Telescope. It's out of commission now, but it continues, its data, despite being several years old now, its data continues to lead to amazing discoveries about exoplanets. And this telescope revealed thousands of exoplanetary systems like these I'm picturing here. And unlike the hot Jupiters that I was talking about before, so hot Jupiters are Jupiter-sized things that are really close to their star, the Kepler Space Telescope revealed smaller planets. It revealed planets that were more like Earth, maybe a little bit bigger. And it revealed them to also be very close to their stars. Like this system here, for example, Kepler 11. So it's called Kepler because it was discovered by the Kepler Space Telescope. And it was the 11th because it was the 11th confirmed system. And this system here, it has 6 planets on the top here. So you have the star in the center and you have these 6 planets around it. And the star is about the same size as the sun. But the planetary orbits, if you put them relative to the size of Mercury and Venus, the inner 5 planets could actually snugly sit inside of Mercury's orbit. So even though these planets are less massive than Jupiter, they're smaller than Jupiter, but they still have this property that they're inside out. These are sort of rocky lava worlds living close to their stars, but they suffer from the same problem of hot Jupiters of how can you get so much stuff interior to Mercury when in our solar system, there's nothing interior to Mercury. So these systems are still inside out. But up until recently, it wasn't possible to measure the misalignment of their stellar spin axis, which is what we've been returning to throughout this talk. The reason is everything about hot Jupiters is easier to measure. The bigger the planet, the bigger the signal. But these systems have smaller planets, so there's a smaller signal. So it was very, very hard to determine whether their stars were spinning in the same direction as the planets or if they were spinning in another direction. So only a couple of weeks ago, well, a couple of months ago, the months go fast these days, only a couple of months ago, this remarkable system was released in the PNAS journal, and it's called K2-290. K2 because it's sort of the second installment of Kepler. The K is for Kepler, and 290, just I guess 290th one. But this system was unique because it had a star in the center that was spinning in one direction, spinning here clockwise. And then it had 2 planets around it. And those 2 planets were in the same plane as one another. So they were in this sort of pizza crust, but they were spinning counterclockwise. So they were orbiting counterclockwise. So this was a system with a star spinning one direction and then 2 planets spinning the other direction, but the same as each other. And even more so, it was found to have a couple of stars nearby orbiting it, which was the picture that I described earlier, that nearby stars cause disks to get tilted with respect to their stars. So this system, it made some headlines: a backward spinning star with 2 coplanar planets orbiting planets in a multistellar system. That's the sort of quick way of saying everything I just said. The star is spinning back upside down. The planets are in the same plane as one another, and there are other stars in the system that could make things wave around. And this is exactly the picture that was predicted by what I said earlier, the idea that you have this protoplanetary disk within which the planets are forming, but you have this nearby star that causes the disk to tilt. So now we can, with this new understanding and this new idea, we can return to Immanuel Kant and he'll be like, this can't be. We have solved it. This is how we can get upside down systems. So, sorry, I'm just checking the time. So this sort of disk tilting pathway seems to be a pretty viable solution. So I went through everything a little bit quicker than I thought, so I'm going to finish a little early, but I'm sure you don't mind. So to sort of recap a little bit, we have this picture of the giant cloud that's sort of collapsing and spinning out and forming planets. And we know it can form upside down and inside out solar systems relative to our solar system. And we can kind of understand how that may come to be. And in understanding how that came to be, for example, I said having a nearby star can cause systems to get flipped upside down. Then you can all of a sudden understand why our solar system might be different, because we don't have another star that caused us to get flipped upside down. And this is sort of how exoplanetary science progresses. We gradually learn about these weird systems, which teach us about all the things that had to go right in order to form our sort of nicely coplanar, everything going in the same direction, stable planetary system that, of course, formed the Earth and life. And so out of this chaos of this cloud, a whole bunch of things can happen, and you can make a whole bunch of different planetary systems. And so I'm going to close with a topic that is close, I think, to a lot of people's hearts, particularly astronomers, and that is the likelihood of life arising on Earth and all the things that might have had to go right. So I'm going to sort of pose a question to you. And how many times do you think, of all the cards of decks of cards that have been shuffled throughout human history, how many times has a deck ever been repeated? Has the same deck ever existed from random shufflings? I wouldn't be asking unless it was really high or really low. And it's really low. It's 0. It turns out if you were to have sort of every human on Earth shuffling a deck of cards once per second for 1 billion years, I don't remember the exact numbers, but you would not yet expect any of those to be the same, because you have 52 things and they can be arranged in 52 factorial ways, which is 52 times 51 times 50 times 49 times 47 times 46. Turns out that's a huge, huge, huge number. That's all the numbers of ways that you can stack a deck of cards to make any particular deck. So if you want to do something new today, you can just shuffle a deck of cards. No one has ever done it the same way before. Why is this relevant to planet formation? Well, oftentimes, and I don't want to like sort of place my opinion on you against a lot of other astronomers, but a lot of astronomers and a lot of people say that the probability that another Earth-like system with life out there is kind of inevitable. And the argument usually made is that we know that almost every star has a planet, and we know there are billions and billions and billions and trillions of stars, so eventually we must get one that looks like the Earth. But because we don't know exactly every single step that must have gone right to form a habitable planet like Earth, we don't know whether the 3 needed to be on top, the Queen of Hearts needed to be next, and so on. We don't know exactly all the steps that needed to go in the right order to make Earth. So we don't exactly know how many stars we need to expect another Earth to repeat itself. It could be 1 million, which in case we're in luck, because there are millions and millions of stars, but it could be trillions and trillions, which would mean that we would need to look through trillions and trillions of stars before we find another Earth-like planet, or before we find another thing like Earth. So I don't know what the answer is. I'm certainly hoping that the answer is that Earths are common, but based on these upside down, inside out solar systems, there's certainly plenty of other decks that have been shuffled through the planet formation process. So as we continue to discover more and more weird things in the sky, just going back to that picture at the beginning of our ancestors sort of looking up at the sky and not even knowing that the Earth rotates, now we've got to this point where we can understand why planetary systems form upside down and inside out in all different ways. And so I'm excited to discover what comes next. So thank you very much for inviting me to talk and listening. And I invite any and all questions. Hopefully I wasn't too short.
I have a question. What's not clear to me is in the beginning, you have a bunch of disk. You have a disk that has a gas, and then it collapses. And I would think that all of the gas would have a vector pointing toward the center of mass of that disk. And it's not clear where the angular momentum arises to begin with.
Sorry, my screen just went weird. Oh, did I just stop sharing? Is that why? Okay. No, that's a great question. So the question is that everything is collapsing, and why doesn't it just sort of just keep going inwards? The reason is
Yes.
Sorry. Oh, the reason is, as I said, with the kind of ice skater pulling in their arms.
Right.
As you need to pull in, you need to go faster and faster.
But where does the initial spin come from? I understand as you collapse it and conserve angular momentum, you'll increase the speed. But initially, if you just have a bunch of gas sitting there and the vector for each of those molecules of gas is pointing toward the center of mass, it doesn't seem like, I don't see where the angular momentum arises to begin with. Even I understand once it's there, if you collapse it, it'll spin faster. But where does it come from to begin with?
No, it's a great question. So it's kind of like if you think of looking at like a pond with like ducks swimming through it or something, you get these kind of little whirlpools here and there. Mm-hmm. It's because this gas is coming out of this turbulent, roiling interstellar gas that some parts are sort of spinning this way and other parts are spinning that way. It's a very slight effect. So these clouds are huge and they're only spinning very, very slightly. But if you were to imagine setting up that cloud such that it's not spinning at all, it would only need a little bit of a flick from nearby gas to start some little tiny amount of rotation. It doesn't need to be much, just a little tiny bit. And then as it starts to collapse, because it collapses so much, by the time it has gotten really small, it's spinning really, really fast. So you just need a little tiny bit of rotation at the start.
But if you started with a tiny bit of angular momentum, and angular momentum is conserved, it seems like you're saying it can increase. Whatever the starting angular momentum is, it is. And I don't see how it gets bigger.
Well, the angular momentum doesn't get bigger, but the spin rate does. You're compressing that angular momentum into a smaller and smaller.
Okay.
I have a little question. Mm-hmm. So these hot Jupiters, or are they all gaseous, or can you have a large planet like Jupiter close to the sun and be rocky? Or by definition, when you get that large, are they all gaseous like Jupiter? And when you get that close to the sun, wouldn't the energetic particles from the sun blow away a gaseous planet?
Yeah, these are good questions. So what you're describing is actually a very, very active field of research. So to answer your first question, we don't expect planets that are as big as Jupiter to be entirely made of rock, because there isn't really enough rock around, for one. Rock is, if you look at these disks of gas, there's 100 times as much gas as there is dust. So it's very hard to sort of make a giant thing of dust without it sort of sucking up gas with it. But another aspect is what I said, that this giant snowball, once it it kind of grows slowly. It's like you're rolling the snowball slowly. But once it gets beyond this kind of critical size, it sucks up all the gas really, really quickly, like within a year or so. It's a really, really quick process. So it's hard to build something as big as Jupiter without sort of, you would need to prevent that gas from like falling onto it first. So just the physics don't allow it. As to your second question of these close stars having their gas blown off them, or the close planets having their gas blown off them, that doesn't happen so much for Jupiter-sized things because Jupiter has a really strong gravitational pull. So its atmosphere is really strongly coupled to it. So no matter how much bombardment it gets, it doesn't really lose a lot of stuff. But planets that are maybe 5 or 6 times the size of Earth, they have smaller atmospheres and smaller gravity, and they do have their atmospheres blown off. So what astronomers are finding is that there's kind of 2 types of planets that are close to their star, 2 types of small planets that are close to their star. There's ones that are kind of like 5 times Earth's size but have no atmosphere, and they're a little closer. And then there are ones that are 5 times Earth's size but have huge atmospheres, and they're a little further from their stars. So there is some evidence that the closer, sort of smaller planets that are closer have had their atmospheres blown away.
Thank you.
I'm going to do a little thought experiment here, if I might.
Yeah.
Okay, let's say I'm an astronomer sitting on Pluto here in our own solar system. Now, Pluto has an inclination to the ecliptic. The orbit of Pluto is 17 degrees tilted with respect to the ecliptic. So if I'm sitting on Pluto and let's say the other planets don't have any appreciable brightness, I will probably never see any of them actually transit the sun. Because the sun at that distance of Pluto, the sun has a diameter of about 1 arc minute, and very small, very bright, but very small. So I'm thinking that we must miss a tremendous number of these exoplanets just because of perspective effects. We will never see them because they'll never transit their star. So there could be an enormous number of small planets out there that we will never see from here because of these effects. Could you comment on that, please?
Yeah, what you're saying is true. We miss about 90% of planets. So if these hot Jupiters, because they're so are these close-in planets, because they're so close to their star, there's sort of a larger angle that the orbit can be in, and us still be able to see them transit. Mm-hmm. But yes, we miss about 90%.
I would think even maybe more than that, because it could be, we're not really in the line of sight of most of these planets that are going to transit the sun or their star. I think we'll just miss them. We'll never see them.
Yeah, but we correct for this. So whenever we come up with a new number of the fraction of stars that have planets, that's not the fraction of stars that are seen to have planets. Right. That's the fraction of stars that are seen to have planets multiplied by some correction factor.
Yeah, I think
that correction factor is this geometric effect.
Probably huge. Anyway.
Yeah, it's about 10 times for close-in planets. So the further away a planet is from its star, the harder it is to see it transit.
Oh, much. Okay. All right. Thank you.
Okay, I'll try another one. So you said in the beginning of your lecture that, and I'm not sophisticated as the rest of you guys, so I'll just use the word tilted, that our Earth is tilted by 23 degrees, and no one's sure why it's that amount. Could be less, could be more. And then you were talking about Uranus and said that, oh, well, it was hit by something, and that's why it's tilted the way it is. Well, I always thought that our Earth is tilted because it was hit by the moon, and a lot of the iron from the moon was left in the Earth, and the lighter material kind of blooped back up again. That's a scientific term, guys. Blooped back up again. And
there are worse scientific terms.
and the lighter material became the moon, and we had a double dollop of iron, and that's why we have a magnetic field, etc., to protect life on Earth and so forth. So But yet you implied that Uranus was tilted because it was hit by something. Is the implication that all these planets are tilted because they were hit by something? Is that what always causes a tilt?
No, their answer is a no, but a maybe. It's a sort of no and maybe. So Earth, the thing about Earth is that it formed by a whole bunch of rocks slamming together. So it wasn't just sort of all the rocks sort of collapsed into one. It was hit by this rock and that rock and that rock, and gradually it built.
Yeah.
And each of these rocks brought in its own angular momentum, its own spin direction. And so the Earth could have ended up sort of tilting 23 degrees just from that sort of random process.
Mm-hmm.
But it could have formed sort of spinning the right way up, and then the moon hit it and tilted it over. We don't really know which one it is. And so the whole moon thing is sort of a very interesting field. It wasn't necessarily the moon that hit the Earth. It was sort of a Mars-sized thing hit the Earth about 4 billion years ago.
Yes,
and
became the moon, yes.
And became the moon. So it
Yeah.
carved off the outer layers of the Earth.
Yeah.
And it wasn't necessarily that it gave iron to the Earth. The thought is that this sort of big splash initiated convection in the interior of the Earth, and then this convection caused the magnetic field. But that's all very speculative. As for if the Earth got hit with something and tilted over, it might be the case. But people don't really talk about it that much. They more talk about the moon formation in terms of how we form the moon rather than how we tilt the Earth. Right. I don't really think people have looked much at whether it could tilt the Earth that way.
So you could have a magnetic field just with convection of non-iron material?
No, it needs to be iron, but Earth would have already had iron.
I'm sorry, but I missed that last part.
Earth would have already had iron without the moon's input.
I see. So Earth would have had a sufficient amount of iron to cause the magnetic field that we have.
Yeah.
Just to move it around a little bit, I see Art. Are you asking a question, Art Firestone?
Yeah, I'd like to ask Chris to say something about the wobble of the Earth's axis.
Mm-hmm.
I mean, it's my understanding that it does shift and change over long periods of time.
Yep. So you're correct. I didn't mention that. So the Earth's axis, it processes around the direction of which it's pointing processes around, and that 23 degrees changes over time, and it changes over about 40,000 years. Mm-hmm. And this is because of the gravitational pull of the other planets in the system, and the sun as well. And so a lot of you may know that this is what causes ice ages to come and go. So ice ages, if you sort of turn the clock back 20,000 years, glaciers went south of Wisconsin. They're about a mile thick, and that was because we were in a glacial maximum. But then go back another 80,000 years or so, and the tilt had wobbled back, and the Earth was as warm as today again. It's sort of a combination of the axis changing and the orbit changing, and we're sort of not sure which one is more dominant. But just going on that, the spin axis changing, I only recently learned that if you look at some ancient monuments that were built by ancient people thousands of years ago, they're sort of built such that the sun will set between two stones at equinox. And because it's thousands of years ago and the Earth's tilt has changed a little bit, the sun sort of misses. So we would assume that the people of the day were good enough engineers to get it right. So the fact that the sun doesn't set in just the right spot now implies that the Earth is tilted a little bit from what it used to be.
Would this wobble imply that other planets have a wobble to their axis? And that the sun is in some period of time shifting its axis? These
are all fantastic questions. So the sun doesn't really shift its axis. The sun's more or less always 7 degrees tilted. It kind of changes the direction that it faces, but it's always about 7 degrees. But the other planets are indeed changing, and the most famous is Mars. So Mars's tilt at the minute is about 23 degrees. It's similar to Earth, but over millions of years, it wobbles wildly from like 45 to 2 and back to 45. It's very unpredictable. And there's sort of a long-standing idea that if the Earth didn't have a moon, it would also wobble wildly like this, and that would make it less habitable. Although that's a contentious argument. There are people who have found the opposite. But the fact is that Mars is wobbling crazily all the time. And this actually causes its polar ice caps to catastrophically melt and then refreeze over millions of years. But at the minute, they're fairly frozen.
I ask a question. Go ahead.
There seems to be a question in the chat.
Hi,
I see.
this is
There seems to be a question in the chat by Eileen. If I could read that. In the planetary system K2290, what are the orbital planes of the 2 circling stars relative to that of the 2 planets? Oh, that's a great question. So I showed that picture of the 2 planets and the central star that was tilted. And we know there's another 2 stars nearby. But unfortunately, we don't know whether it's tilted, whether the plane of that star is tilted with respect to the plane of the planets. If we did, that would help us understand a lot. But just because of the way astronomy gets, you get a lot of projections on the sky, but you don't really see the relative orientations in 3-dimensional space. So I would love to know, but we don't.
Can you comment on if there's a binary star system, whether this phenomenon would occur of inside out?
If there is a binary star, you need the sort of, if you imagine the binary, the 2 stars kind of orbiting each other, they have one plane, one sort of direction of their orbit. That needs to be kind of tilted relative to the disk that's around one of the stars in order for the system to be flipped upside down. So you need the binary orbit to be tilted relative to the disk's plane in order to do it. But once you have that, it's fairly easy for it to happen.
Thank you.
You said that we can detect exoplanet systems where the orbital planes of the planets is different than the orbital axis of the star. Did I understand that right?
The spin axis.
So how can you figure that out?
Okay, well, that was the slides that I skipped because I didn't think I'd have time, but I ended up finishing early. So the way to think about it is that the star is spinning, and that means that one side of the star is coming towards you and the other side of the star is coming away from you. And the side of the star that's going towards you is blue shifted, just like the high-pitched ambulance coming towards you. And the other side is red shifted because it's moving away from you. So if you just look at a star that's spinning, then one side will look redder than the other. So now imagine that a planet is transiting that star. As it transits, it first blocks the blue section, making the star look redder, and then it blocks the red section, making the star look bluer. And so as the transit goes, the star looks sort of red and then blue. But that's if the star is spinning in this direction. If the star is spinning in the reverse direction, then it'll look blue then red, if I got that right, rather than red then blue. And if you see that, then you know for sure that star is spinning in the wrong direction.
Okay, so you can determine the relative orientation of the planet and the star's axis, but not the absolute orientation in space.
You can, if you're really precise, the particular shape, you can get the actual tilt, in terms of 0, 10, 20, and so on. But it's easiest just to get, upside down versus not upside down. But yes, you can get whether it's 30 degrees or 60 degrees or something like that.
Okay, thanks.
Good question.
I have a question about going back to your Kant's theory of the formation of the planets and the idea of a disk. Was that based on is that purely theoretical or speculative, or did he have some observational understanding of, how did he arrive at that theory? Because it seems to be the basis for a lot of research that's come since, if I'm understanding what you said correctly.
Mm-hmm. So I must admit, as I said at the start, I'm not a historian, so I don't actually know exactly what reasoning Kant was using. He wrote in a language I don't understand, so I haven't actually read his work.
Do you know what work it might be? I know his philosophical works, but I don't know where he talks about the idea of planet formation.
I could find it. I don't know the exact name of the book, but I could find it and maybe send the name to Vincent or something, or Victor, sorry.
Okay, I have another question. What do you expect from, or anticipate you'll get from James Webb? Because I know that one of the goals of James Webb is to be able to discover atmospheres around planets, but I'm sure that there must be larger goals than that. And it seems like James Webb would play in very well with what you're talking about now in terms of discovering more of these planetary systems and how they're arranged. Is that how you see it?
Yeah, as far as I know, James Webb isn't going to be very good for getting these spin orbit misalignments, these stellar obliquities. It's really good at getting information about the atmospheres of the planets, but it's not necessarily great for getting the orientations of the stars. But I must admit, I don't know 100% whether it will be able to get any tilted spins. It uses it looks in the infrared, and the technique used to get spin orbit misalignment works better in other wavelengths. But I have to double check that. It's an interesting thought.
All right, in the interest of time here, I'm going to thank you, Dr. Spalding, for giving us a very excellent and interesting and thought-provoking presentation. And we're going to take a break in a few minutes so we have time for Surabhi to talk to us also. So thanks.
I'd just like to add to Victor's thanks there on behalf of the whole club, Chris. That was fantastic talk. We've learned a lot, and we wish you every success in your tenure at Princeton. I hope things go really well, and we'll keep an eye out for stuff coming out of your group. Thank you, Chris.
No, thank you very much. That means a lot. I love giving these talks. So I'm glad you learned something. That's my goal.
All right, then.
That's great. Thank you.
All right. Have a good night.
We're going to have our Unjournal Club presentation this evening. Unjournal, remember, is the spinoff of Journal Club, because really there's no need for this to draw upon highly sophisticated readings and theoretical things, but rather it's subjects and topics that are close to you and close to your heart. And I think tonight's Unjournal Club is a good example of that. Surabhi Agarwal is well known to probably most members who've been in the club for a bit. She is our web head, our web guru, if I may use that term, and does a lot of things behind the scenes to keep that part of our operation going. And furthermore, has been the senior editor of Sidereal Times for a little while now, and has been doing a great job of modernizing Sidereal Times and the software behind it. So tonight, Surabhi is going to take about 10 minutes here and tell us about a topic that we should all be listening to. So Surabhi, take it away, please.
Thank you, Rex. Can you see my screen? Okay.
Yes.
So, well, hello, everyone. And well, before I start talking, I must thank Rex and Mrs. Parker for inspiring me to take this cause and of protecting the environment and starting from my local area. So today, I wanted to talk about light pollution and what we as a group of stargazers can do to curb some of it in our areas. And we are all well aware that light pollution or high levels of sky glow obscures our ability to view most of the objects in the sky. And about 80% or even more of the world's population and almost 99% of the population that of Americans and Europeans live under a sky glow. So we are really not able to watch most of the sky.
All right. We're good.
Okay, so this is my next slide, and here this is a very famous picture taken, if you remember 2003 Northeast blackout, that power outage, and this picture was taken when the lights were on the left side, when the lights were on, and this was taken when the lights went out. And this photo was taken by Todd Carlson, and it became quite famous. So light affects us in many, many ways, as I'll tell you soon. Now, this is another famous picture taken by Babak Tafreshi. This shows the glow of Las Vegas from 90 miles away. It just looks like as if the sun is rising, but it's not. It's late night, and it's how bad the glow is. And the next slide, I'll show you. This is what light pollution actually means. It means glare. This is the glare zone. If you have the excessive brightness. Sky glow, with all the light that is reflected on the sky, and it reflects back to our eyes. Light trespass, if you're sleeping at night and all the light that comes through your windows, that's light trespass. And clutter is bright, confusing, excessive lights all around, like you see maybe in a mall or Times Square kind of thing. So all these are various ways that light can pollute. Now we'll talk about the effects of light pollution. Now, because the planet, all the life on planet exists in a day and night rhythm, diurnal and nocturnal rhythm, for more than 3 billion years. And now for the past maybe 100, 150 years, we have the nighttime darkness that has been overpowered by all the artificial light that we are using. And it's disrupting all our delicate balance in the environment. And studies show that about 35% of the light that is on our outside areas is wasted. And it is poorly aimed or unshielded, and it just goes everywhere, as you can see in the picture below, that all the light is going in all directions, and it's not useful light. And that's about 3 billion per year worth of energy that's lost. And about $10 per year of every man, woman, or child in the US that the light is being wasted. And what it does, it increases our energy consumption. It increases the greenhouse gas emissions, contributes to climate change, increases our energy dependence, and it disrupts the world's ecosystems. Artificial lights disrupt the normal activities of all the of a lot of animals that are nocturnal. For example, the nighttime croaking of amphibians, interfering with thear reproduction cycles, reducing their population. And how many people last summer saw fireflies? There were barely any. And 5-6 years ago, when I moved to this town, in my backyard, the entire backyard used to shimmer with these fireflies. And now, last year, I didn't see any. I saw, like, I could count on my hands. There were so few. So within these last 6 years, so many things have happened to the insect population. And it is very, very important that we take care of these insects, because our own life depends on them. This is another very important diagram
I don't remember you personally, but
that
I did.
that was in the boys and others who wrote this who put this information together, and it shows the life cycle of a moth and how light affects the each stage of its life, from the adult, or let's go down from all stages of life, from the pupa to larva to ovum, and then the and the adult, or the other way around we can go. So every stage of life is affected by artificial lights, whether their feeding is suppressed, their body mass is small, and their mistimed emergence. The mistimed emergence is very important, because as the insects emerge, the birds, or the animals that are dependent on them are waiting for them to emerge. And then what happens is they are mistimed. So mistimed is another reason why all the population of insects and birds and everything is in jeopardy. Artificial lights also have devastating effects on birds. As you can see in this picture that was taken by Ajay and Neelam Talwar. This picture it shows how birds are affected there. Can you see this picture here? It shows how crazy the birds are moving around these lights, because these are migratory birds and they don't know where to go. They just get confused. And so are these millions of hatchlings, turtle hatchlings that are confused by these lights, and they, instead of going towards the ocean, they turn around and go towards the other light, and artificial light, and they just die off. And I think that's not just one or two, those are millions and millions of hatchlings that die, and so do birds. And we too get affected by artificial lights, and it interrupts our sleep, it confuses our circadian rhythms, and it affects the production of a hormone called melatonin, which is released when it's very dark, and that's very important because it allows us to sleep well. And nowadays we have the melatonin gummies available, or tablets available, that sometimes people take, and it's not that great to take all these medications when all you need is a little bit of curbing of this light pollution. And if you don't sleep, then you feel hungry. And you feel hungry at times that you shouldn't, and then you eat more. And all the other things that happens with obesity and heart disease and fatigue and depression, everything affects you. The light affects all these things. So today I actually wanted to implore to all the club members that there are some things that you can do, and that is take these steps to curb light pollution. One, it will allow you to see the sky better, because we all want to watch the sky. And the other thing is, make the township council aware of the adverse effects of light pollution, and you can do it. You go to council meetings, ask for a couple of minutes, and try to inform them that how important it is that this should be taken care of, at least in effective light ordinances can be adopted very quickly, and Rex has done this in his township, and I'm taking his example and I'm trying to do in my township of Monroe. I've gone to the town council, I've talked to them, I talked to the mayor. I have a meeting at the end of this month to talk more about the ordinances. So the attend the environmental commission meetings and try to become a member, because that commission is influential over the town council. It can advise the town council to take these steps, and then educate the township residents by holding meetings or talking to people. One can do that. And I just wanted to tell you that Pittsburgh, a big city like Pittsburgh, is soon becoming one of the first cities in Eastern United States to be dark sky compliant. So it will use all the methods available to reduce light pollution in that city. Now, club members can also help in the following ways in their own local area, that is cut off shielding of outdoor light fixtures that prevent upward glare, and switch off lights wherever you don't need them. Use dimmers, motion sensors, and timers on all the lighting so that they are not on for longer than what you need. And use the amber yellow LED lamps that are like below 3000 Kelvin, the warmer ones, so that they are much better than the colder ones. The colder or the higher temperature ones give out more carbon. Their footprint is more. And preservation of open space and native plant habitat. That is something very close to me, very important, that we should preserve these open spaces so that we have all the insects and other animals have place to that the habitat is maintained, and increase the number of native plants and wildflowers on your property. And if you live in high-rise buildings, use drapes or blackout curtains to reduce bird collisions, because a lot of birds die because they are attracted, they are confused by the light, and they come and they hit themselves on the glass of these high-rise buildings, and actually millions of them die in that sense. So these are different approaches that one can take. One other thing that I'm doing in my township is giving out these seed packets. If you can see them, these are seed packets of native plants, native flowers. And if you want any, just text me or call me or email me, and I can give you a few to plant in your own backyards. And of course, all these things can, like use dim red night lights in your home, save energy at home, take public transport, eat more vegetables, less animal products. That will also create, a better environment. Control light pollution to allow neighbors and wildlife to preserve their circadian rhythms. Switch to an electric vehicle if you can. And of course, renewable sources of energy like solar panels. And now there are some things like community solar panels that you can, that I think New Jersey is, the administration is going for, which means that you can buy from this community solar panel, renewable sources of energy, and it actually lowers down your bill, but you don't have to put those solar panels on your property. So they are somewhere else, like a solar farm, and you just buy a part of it, and that will your electric company will make sure that it gives you a reduced bill. So that is coming up now soon. I think it is being done county by county. I'm not sure, but it is there. If you just Google it, you can see that. And of course, I wanted to tell you that Rex has already done that, and he has, and I also have a copy of the light ordinances that you can take to your own town and ask them to build their ordinances using these as examples. So that's all I wanted to say, that curb light pollution in your own areas, because it is so important. It's one of the ways that we can help mitigate all the effects of climate change in your own local areas. So that's it. Thank you.
Thank you.
Thanks, Surabhi.
Thank you. And I hope that some of you will go to your town council and tell them about it and push them to take these steps.
Yeah, but Surabhi, the big deal going on at town councils around here is when New York City and all the other cities who are, supposedly pro-green and all that are not doing any of this.
Yes, so that's why we have to go and tell them that, and we have to keep pushing. Take your friends with you. We have to just keep pushing them that this is to be done, and tell them the effects of how the adverse effects on our health and on the health of our ecosystem. And if you want any of these slides, you're welcome to ask me for it. And
no, I agree with you. It's just our local councils, even if we go along with this, the major cities aren't doing it. Sort of the same thing with the
absolutely true. And it's just, we've got such a long ways to go. But, for example, come over to Hopewell Township and compare our night skies with West Windsor or Lawrenceville, or take your pick, go over to Hamilton, and tell me that you can see the difference between local lighting ordinances and their lack, because there's a huge difference. But you're right. The overall surrounding area is an absolute ocean of light impending on us. So we got big problems as a society, and we're close to losing it. And we don't want to get all depressed right now at our club meeting here, but I mean, it's true that nature and the animals and the insects, in particular the insects, are taken. The blows to the insect community directly attributable to light pollution. It's a big problem. And as astronomers, it's kind of upon us to help raise the alarm. And maybe we're all tired of being activists. Maybe we weren't ever activists, but we got to do our part. So I really applaud you bringing that to our attention, Surabhi. Thank you. Thank you very much.
I agree. We've got the hidden planetarium people that have to get on board to convince the New York City folks about this. And other major cities.
You would think that the implication I got was that the LED lights helped with the light pollution, and LED lights should also reduce township bills, a power bill. So why wouldn't they rush to implement this?
They are. It's happening. It is definitely happening, and the statistics will prove that. So yes, your points are exactly right on. It's important to pay attention to the colors, the color temperature. Blue tinted was the early rollout of LEDs before it was understood that it created worse sky glow. So that's what happened there.
Nice.
Yeah, amber. Go for amber lights in your outdoor light posts. It's cooler looking too. It's more romantic.
Also with LEDs, there's a lot of upfront costs, which, I mean, the average Joe doesn't get, so
it's evolving though. It is definitely evolving.
Yeah, I understand, but amongst our group, you get the average Joe. He needs a lot of education.
Yeah.
Surabhi, the next meeting you have at the end of the month, is that with the mayor or with the council?
It'll be with the mayor. And council meeting is on Monday, and I'm going to that as well. And I have sent the information to all the council members separately and have spoken to them, and they are all on board. They just need to get to it to write the ordinance.
Yeah. Yeah, can you send me a link and I can like fill another seat at the next meeting? Also, if you need any help with the sitting in on the mayor, Marlon and I
yes.
worked on his campaign and I think he owes us a little.
Yes. Why? How about I take you along?
Fine, sounds perfect.
Okay. We live in the same town.
All right, you guys, stay on it. And we are happy to share those model ordinances if you're interested in taking it to your own township council.
I'd also like to say, Rex, every amateur astronomer should be a member of the International Dark Sky Association, which is the nonprofit that deals with a lot of these issues. Your membership fee will help to contribute to fighting light pollution all over the world.
Amen. What we need is a national and international effort that raises the standard at the whole world level. But all environmentalism and all causes have to start locally. So do your part. And we don't want to get all preachy, but I want to turn the attention to the sky right here and think about what we can do in the future in terms of not only protecting the sky, but observing it. And so what's up right now? Star chart, you guys all have your favorite programs, and I'm just showing this as a way to get our thoughts back to astronomy, where we can see the different symbols here in the color coding. The sky is so replete with deep sky objects, Messier objects, the NGC catalog. There's so many cool things. And with the newer technologies that we're participating in, many of these, even despite light pollution, are becoming visible to us. And so if you guys haven't joined our Astro Video Live sessions this winter, try to catch the next one if you can, or better yet, as spring approaches, get out to the observatory when we're doing this live under the stars. I've marked here right in the upper part, the red circle there, NGC 2403 is a really cool galaxy that's well placed right now for our setups. And we were looking at this and several other things of this type the other night at our session. I was able to keep my camera and telescope running after that session and collected some really deeper hours. So a few hours, not a lot, just really a couple of hours worth of exposure of this object. I just want to show you what you can do from your backyard. Admittedly, this is Hopewell Township, but hey, it's right here in your backyard. And if I can get my slide to advance, and that's questionable.
Oh, wow.
I guess I can't really bring it up full screen.